This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. Developers, are you ready? It's time to upgrade your data platform to InterSystems Iris. Choose your language, choose your tools, choose your environment. Collaborate, build faster, and deploy more efficiently. When you can make faster decisions, there's no telling what you'll create. Ready, set, code. Start coding for free. Visit intersystems.com/try to try Iris.
For Software Engineering Radio, this is Robert Blumen. I have with me today Yevgeniy Brikman. Yevgeniy is the co-founder of Gruntwork, a company that provides a reusable library of infrastructure code written in Terraform, Go, Python, and Bash. Previously, Yevgeniy was a software engineer at LinkedIn, TripAdvisor, Cisco Systems, and Thomson Financial. He's the author of the recently published book, Terraform, Up and Running, and you can see his talk online, Lessons Learned from Writing 300,000 Lines of Infrastructure Code. Yevgeniy, welcome to Software Engineering Radio.
Thanks for having me.
We will be talking today about infrastructure as code design patterns and best practices. We've covered infrastructure as code previously in episode 268, and we'll also be referencing material from 289 on declarative programming in Terraform. Yevgeniy, I'd like to start out with a brief review of the concept of infrastructure as code. What does that mean to you?
I think a lot of it comes from this lovely buzzword, the DevOps movement, where, in the past, you would have a dev team that would write code and write their apps. You'd have an ops team that would rack infrastructure, rack servers, put things together in a physical data center. But these days, that's changed, right? All of the infrastructure these days is living in the cloud, or at least most companies are moving there. And so even the hardware that we're managing is managed through software. So the ops team is writing code to manage all the hardware and all the operations aspects. And so infrastructure as code is just that. It's the ability to manage, to deploy, manage all of your infrastructure using code, which has a lot of really, really nice properties. If this is if there's software engineers listening, I probably don't need to convince anybody of the value of code, but being able to manage your infrastructure that way rather than by clicking around manually in a UI or just running a bunch of one-off commands, using code means things will deploy much faster, much more consistently. It's a lot safer because it's automated. You're not relying on some human memory to get something wrong. The code acts as documentation. You can put it in version control, so you have the whole history of what happened to your infrastructure. You can do automated testing. You can do code reviews. You can reuse code, so you're not doing everything from scratch every time. And possibly most importantly, for me as a software developer, is I much prefer writing and running code than doing a bunch of stuff manually. So being able to manage my infrastructure by running a Terraform apply command just makes me feel better than sitting for 2 hours at the AWS console and mashing up, my mouse button for a while.
Yeah, your finger gets kind of tired when you do that.
A little bit, yeah.
So many of those points you ran through, we're going to be expanding on those in more depth. Those are things which are well known to software engineers, but maybe newer to the world of infrastructure. And so I'm going to circle back around to that. As part of the groundwork here, could you mention what are some of the main infrastructure as code tools and particularly emphasis on Terraform?
Usually when I talk with people about infrastructure as code, there's really 4 broad categories of tools. The first one that a lot of people think of is just whatever they think of when they think of automating anything, which is let's just go write a bunch of scripts. So they bust out in Ruby, Python, Bash, whatever your favorite scripting language is, and you start writing code to do whatever it is you need to do in the infrastructure world, which works well to some extent. You are automating things, you are capturing them as code, but these tools are not custom built for managing infrastructure. You can write code in a million different ways, so you get all these weird patterns that are hard to follow. They don't take into account things like idempotency and what happens after the initial deployment. So usually ad hoc scripts end up being a little bit of a mess. The next category up from that are configuration management tools. That's things like Chef, Puppet, Ansible, Salt, that category of tools that started appearing around, I think, 2008 or so. And so these are custom built tools for managing infrastructure, and they build a lot of things in that make it easier for you. So they have a certain structure that they usually tell you to follow. They do take into account idempotency. You usually have less code to write because the tools have lots of built-in helpers. And so they're pretty powerful, and it's usually a nice upgrade from just ad hoc script. The biggest downside is that the tools themselves get pretty complicated, and often to use them, you have to run extra infrastructure. So for Chef, the canonical way is you have to have some master nodes, and that's extra stuff you have to do and learn and maintain. So another way of managing the software that's on your servers that's becoming more and more popular these days is to use various types of images. So there's Docker images, so those are containers, and VM images, which, to be fair, have been around for a while. And the idea here is rather than configuring a bunch of servers that are already deployed, you actually create a single master image, this canonical, hermetically sealed thing that represents how you want a server configured. And so that thing is a Docker image or a VM. And then you can take this little image, you can version it, and now you can use it all over the place. You can use it in all of your environments, testing, stage, production. You can also run the same code in dev, which is pretty rare to do with the other tools. It's not common to use Chef or Puppet on your own laptop. But running a Docker image or even a VM on your laptop is completely normal. So that's another way to manage your infrastructure. But all of these tools I mentioned so far, they're focused on, okay, I have a server and I want to install Linux on it and these 5 pieces of software that I depend on. Question then is, how do you actually manage all the infrastructure under the hood? How do you get those servers in the first place? And that's where provisioning tools come in, such as Terraform and CloudFormation and a few others. And so these tools are custom built for defining the underlying infrastructure layer. That's all the servers, the networking layer, load balancing, databases, DNS, etc. And these tools are probably the newest of the bunch. I think Terraform has been around since maybe 2014 or so. But they're filling a very important niche, which is, as we move to the cloud, we need a way to manage all of this underlying infrastructure as code. And Terraform has become a very, very popular way for doing exactly that.
In your book, you provide some estimates for how long it takes to develop infrastructure as code projects from scratch. On first reading these, they seemed rather large, but they're consistent with my experience. But I also can't help thinking that it really shouldn't take that long. I want to start out with give some numbers for how long these projects take.
It certainly varies on what you're doing. And the numbers that I have in the book focus specifically on somebody that wants to use this infrastructure in production. In other words, you're not building just a side project. This isn't just something for your, just for having fun. This is something you're betting your company on, right? Thousands, millions, billions of dollars are at stake. So if you're going to production, there are a lot of things you have to take into account, and building all of that out takes a significant amount of time. Rough numbers, and to be honest, these are probably best case scenarios, but roughly speaking, if you are using the cloud, you're using AWS or Azure or GCP, and you're using a managed service, something where the cloud provider has already done most of the work, you can probably get that thing production ready in a couple weeks. But if you're using a cloud provider and you're going to be building your own distributed system on there, if that system is stateless, so it's not storing any data locally, it's maybe shoveling it out to some database, like a bunch of Node.js apps. Now the amount of time it's going to take you to go to production will typically take about twice as long. So maybe 4 weeks, 6 weeks, something like that. If the distributed system is stateful, so you want to spin up, the Elk stack, so Elasticsearch, Logstash, and Kibana, and these are all writing to disks, and you probably don't want to lose that data. Now we're going to go up a whole order of magnitude. Now we're talking months. This could be 2 to 4 months to get a system like that ready for production. And finally, if you're going to be spinning up your entire cloud architecture, so all of these managed services, your own stateless distributed systems, your stateful distributed systems, all the wiring in between to connect everything, and CI/CD pipelines, and so on and so forth, We're talking 6 months minimum to do it from scratch. And for larger companies, usually a whole lot more. 24 months, 36 months would be pretty normal.
Do you think the time reflects the complexity of what you're trying to do, or is it because these tools don't quite work as smoothly as possible and you spend a lot of time fighting with the tools and the environment?
I think there's a lot of factors. I think the two main ones that I've seen that cause this stuff to take so long is one is what you're mentioning. So it comes down to the tools and just the fact that DevOps is new. And so a lot of the tools are fairly immature. They're new. There's a lot of patterns we're still figuring out. And so for various reasons, DevOps is really susceptible to this concept that is delightfully described as yak shaving. For people listening who have not heard this term, I think you're going to enjoy it. This is one of my favorite terms, and anybody in the software industry is going to be very familiar with it. So yak shaving, the idea here is it's all the little things you have to do before you get to work on the thing you actually wanted to do in the first place. The canonical example in my mind comes from Seth Godin's blog. He has a blog post specifically about yak shaving. And he gives this kind of really wonderful example where, you wake up one day and you decide, okay, I'm going to go wax my car today. And you head outside, you go find the hose, and you find out that the hose is broken. Okay, no problem. You'll run over to the hardware store, get a new hose. So you get in your car, you're just about to head over to the hardware store, and you realize, okay, there's a bunch of toll booths on the way. I need one of those easy pass things, so I'm not spending all my day paying tolls. So you look around for the easy pass, can't find it, and say, no problem, I'll borrow the easy pass from my neighbor. You're just about to head over to the neighbor's house when you realize, oh, wait a minute, I just borrowed a bunch of pillows from him last week. I got to return those first. So then you go dig through your house to find the pillows, and you realize all the hair, all the yak hair in those pillows has fallen out. And so the next thing you know, you're at the zoo shaving a yak, also you can go and wax your car. So that's yak shaving, right? It's just all of this stuff you have to do that seems to get in the way. And programming, we see this a lot. You wanted to go deploy some simple piece of code, and somehow 2 weeks later, you're fixing a TLS certificate halfway across your code base. But DevOps in particular seems susceptible to this because I think the tools are fairly primitive. They're really tightly coupled. Every time you touch something, it feels like pulling a wire out of a box of wires. It kind of drags everything else with it. And so things really take a lot longer than you expect because of that.
Yeah, we've all been there. Now we've reviewed some of the problem domain. I want to get into the main focus of this talk. You hit on some of these in your intro. The software engineering community has developed a lot of knowledge about software development best practices, some of which could be applied to infrastructure as code. And that's one of the main focuses of your book. I want to start out with the idea of modules. Why do you advise the use of modules in Terraform?
So modules in Terraform are very similar to functions or classes in a general purpose programming language. So if you're using Java or C or Python, you're probably used to breaking your code up into a bunch of small functions and classes. So in Terraform, breaking things up into modules pretty much serves the exact same purpose. You're trying to write code out of small pieces where each piece does one thing and does it well, right? That's not a new concept. That's the Unix philosophy. It's been around for ages. You break things up into modules so that you can reuse your code, just like a function. You write the function once, you can now use it in 20 places in your code base. Same thing with modules. You use it so that you can compose your code. In other words, you can build more complicated things out of simpler pieces. So you create a simple module that does X and a simple module that does Y, and then you can combine the two of them together to do something more complicated, which is, X and Y or X times Y. You do it to hide complexity. So, you can have a very simple function that under the hood does something truly complicated and difficult. And all of your users benefit from, a single one-liner to do something that's actually pretty hard. Same thing with modules. You create modules to encapsulate, to abstract away really complicated infrastructure. And modules also tend to be a really good abstraction layer for testing as well. So with general purpose languages, functions, you would write a bunch of unit tests for them. It's a good way to build your code out of these really battle-tested, understood pieces. It's the same thing with modules. If you build your code out of small modules and you test each of those modules, then you're building on top of these really solid building blocks.
These are some of the same reasons why people use functions and classes in pretty much any language.
Exactly. Yeah. I mean, it's infrastructure as code. Code is code, and pretty much all the same principles you'd use in Java or Python or Ruby are going to apply to Terraform and almost any other infrastructure as code tool.
Another concept we have from software engineering is layering. How does that fit into the Terraform world?
In a pretty similar manner, in the sense that typically with modules, you'll have. I will say that the term module is a little overloaded in programming in general, but in the Terraform context specifically. So module can be used to refer to, maybe I describe it as a generic module. So that's something that does some type of infrastructure, but it's not specific to some use case. So maybe you have a module that deploys a single server or a group of 5 servers. And there's nothing specific about it. That's just a generic way that your company is going to run this group of 5 servers, and maybe they'll be highly available and scalable and have certain types of monitoring already configured for them. Then a layer above that is you can start building modules that are a little more use case specific. So maybe you create a microservice module that takes that cluster module, maybe it adds a load balancer module, maybe it adds a database module, and this is how your company runs a microservice. And then finally, at the layer above that, you can have a root module, is technically the term in Terraform. And that's the actual thing you deploy. And that's going to be very, very use case specific. So that'll be a root module to deploy service foo, maybe your search service at your company, and another module to deploy your MySQL database, and another root module to deploy your network topology. So you essentially, just like you might combine functions and classes and layer things together in any general purpose programming language, you can do the same thing in Terraform and layer together these pieces to gradually build up complexity.
Module is a keyword in Terraform that provides a specific way to reuse code. Layering is a design pattern where you divide your system up from top to bottom such that each layer communicates with adjacent layers. Now, you provide an example in your book or one of your talks, I forget, of building out a Vault implementation, Vault being a HashiCorp product. How do you go about breaking something down into layers, which go from bottom to top, and reusable modules that you might call multiple times to compose things horizontally?
Yeah, that's absolutely right. So module is overloaded, unfortunately. So module is a keyword in Terraform, like the language. And when you use it, you can basically say, hey, go find the code in this folder or this Git repo and run it. Module is also used to refer to the thing you deploy. It's also used to refer to other things. So it's unfortunately a slightly confusing term. But you're right, layering is more of a design pattern. If we look at a concrete example like Vault, so what is Vault? Vault is an open source tool from HashiCorp for storing secrets. Things like database passwords, TLS certificates, API keys, anything you don't want the bad guys getting. And it runs as a distributed system. So you typically run 3 or 5 Vault servers, and those typically talk to 3 or 5 console servers to store the actual underlying data. And so it's actually 2 distributed systems you're running. So we built a set of modules to run Vault. We did that in partnership with HashiCorp. And the way we design them, if you actually go look at the code, is there isn't just one super magical Vault module that does everything Vault. Instead, it actually consists of a bunch of small little pieces that each do different pieces of this Vault equation. So for example, one of those pieces can spin up a Vault cluster. In other words, those 3 or 5 servers specifically to run Vault. Another piece can spin up a load balancer. Some customers use load balancers with Vault, some do not. Some talk directly to the underlying nodes. There's another module for the security group rule. In other words, the firewall rules that control what traffic can go in and out of Vault. Another one that controls IAM permissions, which is the things the Vault nodes are allowed to do. And the reason we have these all as separate pieces, as separate modules, is that depending on how you're deploying Vault, you will want to be able to combine and compose those things in different ways. And I don't mean just across totally different companies. I mean, even within a single company. So the canonical example is in production, you run Vault the way I mentioned earlier, 3 servers for Vault, 3 servers for console. In a pre-production environment, that's a bit expensive and you don't need that much scalability and high availability. So you might want to co-locate Vault and console onto the same cluster of servers, or maybe even just a single server. And if Vault was one super module, there'd be no way to do that. But because the security group rules are separate, because the IAM permissions are separate, because the load balance are separate, now we can choose to combine those pieces with the separate pieces of the console code that we've written. And so you can use the same code in different environments in different ways. You might also run it in different ways between a PCI environment and non-PCI, et cetera. So by building it out of these little pieces, you can then layer them together to meet different use cases.
If I understand what you're saying, these reusable components, they're building blocks, and you combine them, but maybe parameterize them a bit differently in order to create the whole. And you might combine them differently or with different sets of parameters to do a similar thing in different environments.
Exactly, yeah. And this ties again into a lot of software engineering practices you're going to see with other languages, right? You create functions, you create classes, but you also do things like dependency injection, where in a general purpose language, instead of the class that you wrote deciding I'm going to talk to a MySQL database, you pass that in as a parameter to this class. And so with infrastructure code, you can do the same thing. The Vault code, for example, takes in as an input parameter what VPC to run it. In other words, the networking setup where it's going to live. Rather than just assuming or creating one itself, you can pass one in. And that way, you can run it in different VPCs. You're not subject to some very specific way that code designed it. It's actually something you can control, you can inject. Turns out that also really comes in handy, both with general purpose language, where you can then inject mock dependencies rather than the real ones. And you can do the same thing with infrastructure code. You can use some default VPC that you use for testing rather than a production one at test time.
I do want to come back to testing. I want to talk a bit about the idea of a VPC. In some of the examples, you have a module that defines a VPC, and that functions in a design sense as a layer, and then you put your components in the VPC. So you're building up your final system in layering. Could you explain the thought process around that?
Yeah, so there's actually something else that comes in that is a little more specific to infrastructure code that's also worth considering. So the VPC, for folks that are new to this, that's your basic networking setup in usually in the cloud. Every cloud has its own different types of VPCs. It stands for Virtual Private Cloud, and it consists of things like subnets and route tables, and basically figures out IP addresses and what IP addresses can talk to what other IP addresses. So the VPC is usually one of the very, very first things you're going to create inside of your AWS, GCP, Azure account. And then you're going to deploy everything else into the VPC. And that way, when you deploy a server into it, that server gets assigned a reasonable IP address. So one of the things that tends to happen is the VPC is probably something you're going to deploy once, and you probably aren't going to touch it a whole lot. Maybe you'll update it once a year or something like that. It might sit there for years without you having to do anything to it. Whereas the things you deploy into the VPC are going to change much more frequently, right? If you deploy your Dockerized app into the VPC, that might change. You might redeploy that 20 times a day. So one of the other interesting things about separating your code into these different modules is, and this is again part of the overloaded terminology. So this is actually specifically root modules. These are the ones where you actually run Terraform apply to deploy them. Is you might want to separate the VPC root module from other things. Because if they're together, and this is actually a really common mistake, people who are new to Terraform, new to almost any infrastructure as code tool, is they tend to shove all their code into a single file or a single folder, basically a single module, and that code grows and grows and grows. It has all your environments, all of your different types of infrastructure, all in one place. And that has a huge, huge number of downsides. If all of your code is in one place, it is going to be slow. Running Terraform plan or apply could take 20 minutes, or just the plan, even just to fetch the data about all of that infrastructure. It's insecure because now if anybody wants to change that code, they have to have permissions to everything in that code. It's hard to understand and review because it's just a huge amount of code. And even if you run Terraform plan, it's a giant output that nobody really looks at. It's hard to test. I mean, infrastructure testing is hard anyway, but testing a large amount of infrastructure is borderline impossible in any automated sense. And most importantly, it's extremely risky. If you have your VPC code in the same place as the app you deploy 20 times per day, then 20 times per day, you put your VPC at risk of some sloppy little thing, some little typo, some silly mistake, and you could blow away your entire network topology and everything running in it. And there's just no reason to do that. And so this is something specific to infrastructure, right? Because mistakes with infrastructure tend to be more costly than mistakes with applications. You have a bug in your application, most of the time it's pretty harmless. You deploy an old version or a new version, you're good to go. You mess something up in your infrastructure and your company could be out of business. So the mistakes are costly. And so you do a little more thinking about how to isolate your code, how to separate different things. And so one way to do that with Terraform is to deploy these things in separate root modules. And so the VPC is in one root module, your apps are in another one. When you deploy them, the permissions you need to access them can be different. The state that Terraform stores about this infrastructure is stored in separate files. You can have different approval and code review and testing practices for each one. And so you can basically separate things out to essentially control your level of risk. And so that way you can go and deploy your app 20 times a day and not have any worries that you're accidentally going to blow away a VPC.
There's a number of benefits to this approach. You're talking about, for one thing, security, in that everyone doesn't need to have permission to everything. And then there's the efficiency that when you deploy your service, it doesn't have to do a verification of the state against 1,000 pieces of infrastructure, which you as a engineer who's building one service are not intending to change those things anyway.
Right, exactly. Don't put all your eggs in one basket, right? There's nothing new here. It's something humans have known for a long time. It's just tempting to do it with infrastructure code because it's new and we don't understand it as well. But if you find yourself with 20,000 lines of infrastructure code in one file or in one folder and it's all running together and plan is taking 10 minutes, you should probably refactor and change that because you're going to have a bad day sooner or later from that.
Where I think we are going or could go with this discussion is talking about a microservices architecture, which is increasingly popular. The way Terraform works, it runs all the Terraform files in the directory where it runs. So you have different code bases, which are either in different Git repos or just different directories. What is a recommended structure for an organization that is delivering a microservices architecture?
Yeah, microservices is interesting. It has some of the same trade-offs, right? What are the reasons to do microservices? One, because you read about it and it's a buzzword and you think it's cool. That's probably a pretty bad reason. The actual reasons to do microservices are things like you need to scale your teams. Actually, it's not even a technical thing. It's actually a social thing, right? Because you have a bunch of people and they, having 10,000 developers working on a single app is pretty hard. They end up stepping on each other. Some want a lot of testing, some want to just push 100 times a day without any testing. So allowing teams to own separate services and to go at their own pace and control their own coding practices, that's a really nice benefit of microservices. And the same thing may apply to infrastructure code, right? You could have one team that's responsible for the VPC and they have their own coding practices and their own testing practices and they can use those. And you have a separate team responsible for a certain microservice or a database and they can use different practices. Another reason to break things up is so you can use different technologies with microservices, right? You can write one in JavaScript and one in Python and one in Java and one in Ruby. That one probably doesn't apply quite as much to the Terraform world because you're probably using Terraform here and Terraform there, but it could. So one of the patterns, for example, that you might see is you might use Terraform, for example, to deploy Kubernetes. So the actual servers, like the worker nodes, the control plane for this orchestration tool for Docker. But then you use Kube Control or Helm or some other tool to actually deploy the Docker containers on top of Kubernetes. So there you're using two separate tools by basically separating things out. The third reason to use microservices in the world is for different scalability requirements. So you have one service that needs a lot of memory, another one that needs a lot of CPU, one that scales vertically, one that scales horizontally. So breaking those out separately allows you to scale them each individually and appropriate to whatever needs they have. Whereas if they're on in one giant monolith, you can't do that. That one probably applies the least to Terraform code. Terraform code you break out mostly to maintain risk. Which is, by the way, another interesting property of microservices when you do them correctly is one part, one microservice could go down. And if you've built your microservices correctly, the others can keep running and function, and that's fine. And that's the same idea with separate root modules in Terraform is if you blow something up in one module, you kind of limit the blast radius so it doesn't affect all the infrastructure in the other modules. If you're running microservices using Terraform, how you organize the code, as always, the answer is it depends. But the general idea here is you want to keep those factors in mind. Is do the teams that own those microservices need to run separately and at their own pace? So if one is deploying using Terraform 30 times a day and one deploys one time a year, that would be a good reason to separate out their Terraform code. Another one comes down to the risk tolerance of what happens if things go wrong. If you have one module that has your microservice that processes payments, and you have one that has like a front end funny widget that you put up for April Fools, then maybe the one, when you're updating the one for April Fools, you take down your whole payment system. That probably isn't a good way to manage risk. You may want to separate those microservices out. So factors like that are what you would keep in mind in terms of how you organize the code. But just as with microservices, the thing to keep in mind is it's a balance. Microservices have a cost, and it's actually a very, very significant cost. And similarly, having a ton of Terraform modules also has a cost. It's more stuff to manage. You basically have to connect modules together, which isn't the easiest thing in the world to do. If you have to deploy a new environment, it's easier to deploy it when it's just one module versus 300. So it's a balance. You don't want to go crazy and have 8,000 Terraform modules per environment, just like you probably shouldn't have 8,000 microservices per environment. So strike a reasonable balance in terms of like risk tolerance and how your teams are operating.
Calling all developers. There's no telling what you can create when you upgrade your data platform to InterSystems Iris. Are you ready to build the applications you want, however you want them? Are you ready to develop applications faster than ever? Collaborate, build faster, and deploy more efficiently. Tomorrow's next breakthroughs are waiting for you today. InterSystems Iris Data Platform. Ready, set, code. Start coding for free. Visit intersystems.com/try to try Iris.
We recently published a show on data management in the world of microservices. Some microservices are necessarily going to be stateful, and they may require some kind of storage infrastructure. Each microservice may use a different type of data management. One might be relational, one might be a key value store. And the microservices, they need some infrastructure to run on. Do you have any thoughts on a couple different structures for teams? One would be you have the Terraform code separate, DevOps engineers are deploying that. The team that's building microservice, they need a DynamoDB, so they communicate with DevOps. DevOps pushes it out, then they deploy their code. Or option B is you have maybe an embedded DevOps engineer in the microservice team, or maybe developers learn a bit of Terraform and they manage their own infrastructure and they push it out as part of an integrated deploy along with their code. What are your thoughts on those two options?
Yeah, we've seen a few different patterns. Again, the boring answer here is it depends, but the more interesting answer is probably the most effective pattern we've seen is if a central team can build up a considerable amount of expertise around Terraform and whatever type of infrastructure you're using. So maybe that's AWS or Google Cloud or Azure. And it takes actually a while to build up that expertise, to understand whether things should run on EC2 instances versus Docker container versus Lambda functions. How do you secure these things? How do you do the monitoring for them? It's a lot of stuff to learn. And so often the pattern that we've seen work pretty well is a central team builds up that expertise and creates a bunch of reusable modules that implement the basic requirements for this company. So if your company has to be PCI compliant or HIPAA compliant, the modules will implement those requirements and will only use services that are valid for those constraints. And if you're using Kubernetes, the team will write code that deploys to Kubernetes the way that your company wants to deploy. If you're running on top of VMs and auto-scaling groups, the modules will do that. So you create these basic set of reusable building blocks that are well-tested, well thought out, and basically have the guardrails in place. And then you hand those to the other teams to then basically do a self-service kind of a setup where they can then use that to deploy their apps. They have some ability to customize things as they need it. They're not completely dependent on this one centralized team being a bottleneck. But under the hood, they're still fulfilling the basic requirements for your company. And how much of a central team you need tends to increase with the size of the company. So if you're a 3-person startup, well, honestly, you probably A, shouldn't be using microservices, and B, you should probably be on Heroku or something like that and not AWS. But if you're, let's say, a 10-person startup, you probably don't need, more than like a single person who spins up a few basic things and then everybody else uses those pieces and deploys with them. But if you're a 10,000 person company, you probably want to have a significant team that really thinks through these things and then gives this nice menu, this service catalog essentially of reusable code to the rest of the company to use. And then the rest of the company uses that to then spin up their microservices, spin up whatever it is they need to. And you can all be happy that things are working more or less as intended.
I want to change directions here a bit, move on to another software engineering concept, the idea of releases. How do you advocate the use of releases in infrastructure as code?
I'll explain how we do it at my company. I'll actually walk through the whole process. So all the code we write goes through pull requests. So any change you make, you spin up a new branch, make your changes, and then submit a pull request back to master. All the code gets reviewed, and all of the code goes through our suite of automated tests. And assuming the code review goes well and the tests all pass, you then merge the code to master, and then we do a release. Now, what we mean by release is, GitHub has a thing called a release, but under the hood, it's a Git tag. So we're basically creating a tag pointing at that commit that we just merged to master, and that tag has a version number. And we use semantic versioning, so it's version x.y.z. And we try to use that version number to communicate whether the change is backwards compatible or not. In the case of Terraform, for example, if you had a module that used to create a certain resource and now it doesn't, that would be a backwards incompatible change. Or if you had a module that took in a certain input variable and it no longer does, again, that's a backwards incompatible change. Any consumer of that module now has to update their code in a non-trivial way in order to use the new version. So we do this release, we create this Git tag with a version number, as well as some release notes, migration instructions if you need them. And now this code is available for use. So in the case I mentioned before with the central DevOps team building out a library of code for the rest of the company to use, that team could do the same thing. They could create their microservice module version 0.0.1. And then a few teams deploy with that. And then the ops team improves something in the module and they release 0.0.2. Now the rest of the company can pick up the new version. And hopefully all they need to do that is just bump a version number from 0.1 to 0.2. So it should be easy. And you would roll this out by promoting that change from environment to environment. So you would take version 0.0.2 and you would deploy it in, let's say, your dev environment. Test it, make sure it seems to work, there's no issues. If that works, you then take the exact same code, that 0.0.2, and you put it in staging. Again, test, everything looks good. Finally, you take the exact same version and put it in production. And this is immutable infrastructure, so these immutable artifacts, these tags, ensure that you're running the exact same code in all of these environments, which gives you a slightly better chance that if it works in one, it'll probably work in the next one. So that's our typical release process.
Now, suppose in production, we are running 10 different microservices. Your module does something that is common. Let's say it spins up a load balancer. All your microservices need a load balancer. And you said previously you may have the one that releases 30 times a day and the one that releases once a month. Is it necessary that everybody upgrade to 0.0.2 right around the same time, or can we slow roll it out?
This is the classic question that I think every company runs into, not just with infrastructure code, but with anything. If you have an internal code base of Java libraries that you share within your company, you're going to have the same question. Does everybody update to the new, security library now, or do we do it one at a time? This happens all over the place. The answer comes down to, as always, it depends. So what does it depend on? One factor is what kind of a change is it? If, for example, the central team released a security patch and it's patching something critical from a security perspective, you, of course, want everybody to pick up that change as soon as humanly possible. If it's something a lot more minor, then it's less critical that you do it immediately. And now it comes down to what are the trade-offs? If people don't pick up the change immediately, the advantage is they're able to focus on whatever they were doing originally, shipping product, for example, rather than updating their infrastructure, which the product team might like. But on the other hand, if you have some versions of the services that are now way, way, way behind, then it's going to be harder to catch them up. They're going to be out of date. And when that inevitable security patch does come out, it'll be really hard to get that team up to date. So it's a balance, as always. Do you want to pay off tech debt? Do you want to ship product? What is your team going to prioritize? Generally, if you're using semantic versioning, you can probably, if your tests are good, you can probably safely update patch versions, maybe even automatically. So if your central team goes from 0.0.1 to 0.0.2, you can maybe push that change out immediately to everyone. if your testing is good enough. And it's a backwards compatible change, so that shouldn't do too much damage. But anything beyond that is going to take testing. It's going to take time to roll out. And that's where you're going to have to make a business decision. That's really what it comes down to.
It is common in the world of server configuration management, the Puppet, Chef, Ansible, that you would run those tools on the server every, say, 30 minutes, and any changes that anybody makes manually would simply get overwritten. Do you advocate that with Terraform? And it is a way to really enforce that infrastructure as code culture where any changes you make are going to be overwritten? Or do you advocate more of what we seem to be talking about, which is releases, where we say we have a change, we are going to decide to put that change out now or tomorrow?
Yeah, with tools like Chef and Puppet running every 30 minutes or what have you, the reason that works, and occasionally that causes its own issues, but for the most part it works, is because we're changing the configuration on an existing server. Right, you're updating some dependency on your Linux box, and most of the time that'll work okay. And even if it doesn't, the damage will usually be not catastrophic. With Terraform code, what you're managing with that code is the server itself, as well as the network it runs on and the database next to it and the load balancer and all your DNS entries and everything else. And so the cost of getting it wrong there is a lot higher. So the trade-offs are different. If you were to automatically push out some DNS change, and you could conceivably make your entire website inaccessible if there was a small bug. If you automatically were to roll out database changes, you might delete your company's data. So generally speaking, I think the applying Terraform every 30 minutes is not a pattern that you're going to see very often, just because the cost of getting it wrong is really high. What you might want to do on a regular basis is run the Terraform plan command. And what that will show you is the difference between what's actually deployed in the wild and what your code says is deployed. And if the plan basically shows any difference that you weren't expecting, that probably means something is out of date. Somebody did make a change by hand, or there's some kind of issue going on. And that's a good way to gauge the health of your code. But ultimately, fixing it is still going to be a human being having to make a decision and say, hey, the reason there's a difference here is actually legitimate and we shouldn't do anything about it. Or, oh, whoops, I tweaked this manually and forgot to sync up, and let me go fix that. And you can create alerts around that. You can actually do things to detect it. But I don't know that I personally would not have confidence in auto applying every 30 minutes. I think that's going to end up with a lot of really uncomfortable discussions with your CEO when data starts disappearing or the site goes down.
Yeah, I have seen certain amount of chaos caused even by Puppet being applied on a continuous basis. So moving on, another best practice from software engineering is code reviews. How can code reviews be applied to infrastructure as code projects?
More or less in a similar manner to code reviews on any other kind of project, which is first thing you do is you create a culture where you decide what requires review. You could simply decide all code changes require review, or maybe certain parts of the code base. That's up to your company. That's another good business decision to make. Once you've decided it, you need a code review tool. If you're using GitHub or GitLab, Bitbucket, all of these now support a pull request or merge request process, which inherently includes a code review. So you typically don't need separate tools these days for that. Next thing you'd probably want to take care of is to determine the standards, right? You don't want people just code reviewing randomly, because that means one person will do a review and will nitpick every tiny little minor thing that's totally irrelevant, and then the next person will just say, ship it to every single PR without looking at it. Come up with some standards for what the team is looking for. One of them could be things like, does this thing have automated tests, right? That could be a human being say, no tests, not going to give it a ship it. Does this thing have documentation or example code or comments or some way for somebody new to figure out how to use this code? Something that should be part of your standard is the code style, but you probably don't want a human being enforcing that. You want to use an automated tool. So in the case of Terraform, you can automatically run Terraform format. It's just one of the commands built in, and that'll automatically style the code in a certain pattern that's consistent across your code base. You definitely don't want to spend time arguing over curly brace placement or anything like that. So all of that, I think, is very common with almost any language. The only, I think, special thing about Terraform that you might do differently in your code review process is to include the output of the Terraform plan command as part of what you review. So you're reviewing not just the changes, but also Terraform's output, which shows you what those changes are going to do to the live environment. And those changes, the output of Terraform plan, they look a little bit like a git diff. So they have like pluses and minuses and tildes to say something is being added, removed, or modified. And those are really nice to have as part of your code review process, because then you might see, a big red minus sign next to your database and say, wait a minute, don't ship that thing. That's not going to end well. So making plan part of your code review process is, I think, somewhat unique to Terraform. What it looks like in practice, if you set up a nice pipeline around Terraform, is team member will, for example, put up a pull request with a change to your dev environment, and you might get like a Slack notification that says, hey, here's the pull request and here's the plan output. Do you want to approve these? And you can, click a button in Slack or whatever tool you're using that approves it. Then that change goes out. You test it, make sure it works. Then you repeat the same process in staging, and then you repeat the same process in prod. And every step of the way, you're checking the plan output and the code changes. And you might notice again here that we're being extra cautious with our infrastructure changes, right? If you were, for example, rolling out a new version of an app, you probably don't need a human being approving the rollout to your Kubernetes cluster, your auto-scaling group every time, because those rollouts almost always look the same. And if they go bad, it's pretty easy to roll back. But again, infrastructure has a cost of getting it wrong that's quite a bit higher. And so that's why you want a human being to use a little bit of judgment to look at these plan outputs and say, okay, yes, this should ship to prod. This probably isn't going to do anything too catastrophic. So build that into your pipeline, build that into your code review process, and you can sleep a little more in the evenings.
Yevgeniy, if I was going to start a task in any programming language and I need to do things like talk to a database or manipulate date and time, I'm not going to code that all up from scratch. I'm going to type into Google what's the best library in Python for database client or whatever it is I'm trying to do. I found even in working with Puppet, there are Puppet libraries for almost any type of server you might want to manage. You may want to modify that library, but it's still going to save you a lot of time versus starting from scratch. Where are we in the Terraform world in terms of reusable open source ecosystems?
So Terraform has something called the Terraform Registry, which is a collection of open source reusable Terraform code. Very similar to probably what you're mentioning. There's, I think, the Puppet Forge, there's Ansible Galaxy, there's Chef Supermarket. There's a bunch of these collections of open source repos. To be honest, the quality of the code in those is a mixed bag. Some of it works beautifully and it saves you a ton of time, but a unfortunately high percentage of it, I'd say a much higher percentage of it than you'll find, for example, in NPM for JavaScript or in Ruby gems for the Ruby world or in Maven for Java. I think a much higher percentage of infrastructure code has issues. A lot of it just does not work at all. Like you run it and it just doesn't do the thing it says it'll do. It's completely broken. A large percentage of it is very, very hard coded to one specific use case and might not fit what you're trying to do. And I'd say an astonishingly high percentage of it has no documentation and no automated tests. So to me, that's a bit of a problem. And before I started Gruntwork, actually, we spent a lot of time looking at all of these, trying to use them. I've tried to use them in my previous projects, and my success rate has not been great and is still not great to this day. And I think the biggest issue is exactly that. There's really two core problems with a lot of the open source code. One is the lack of automated tests. Automated tests for infrastructure code are hard to write, they're hard to maintain, and most of them are actually integration tests that have to deploy into a real Google or Amazon account or Azure. And so they cost money. And most people just don't want to spend money on their little open source project. So most of those projects have no testing at all. The second major issue is a lot of them are not meant to be used directly in production. They're meant to do exactly what you mentioned, which is you're supposed to copy and paste them and then adapt them. And then you basically never touch the open source repo again, which means you don't have this feedback cycle of people using it on a long-term basis, getting updates, getting new versions, because that's not how you consume most libraries, right? If you're using Java, you're pulling in jars from Maven at a specific version. If you're using Ruby, you're pulling in Ruby gems at a specific version. If you're using Node, you're pulling in libraries from NPM at a specific version, and occasionally you bump those version numbers. You're not pulling in the raw source code and modifying it in place. That's not the normal way to use open source code. Unfortunately, a lot of the infrastructure code out there is designed for pull it in, copy and paste it, basically fork the open source repo and then never, rejoin it again. So there's a bunch of issues at my company at Gruntwork. The stuff we open source, we do try to work around a lot of that stuff. So we do try to test it. We do try to document it. It is designed for use directly in production via a versioned URL, but it's still, I'd say the ecosystem is still developing, to say the least. So it's still pretty hard to just quickly Google something. I need distributed system X. I don't want to spend 6 months, building that myself. Can I find it off the shelf? It's hit or miss. It's very hit or miss.
Go back to the Python example. I think every Python program that wants to connect to MySQL pretty much wants to connect to MySQL in the same way. The SQL statements you send will be different, but there isn't generally a problem of this SQL client library doesn't connect to MySQL the way I want it to. Now, is it the case in building infrastructure that everybody's needs are, if not the same, at least the differences can be expressed maybe through choice of parameters? Or do people build infrastructure in sufficiently different ways that it's just hard to come up with a reusable module that will be generally useful?
I think there is just as much overlap in how people use infrastructure as there is in almost any other kind of programming. You're never going to have a module that fits 100% of use cases, just like you're never going to have a Java library that fits 100% of use cases. But 80, 90 plus percent, I think, is very likely. I think the issue is you have to design it the right way, and you have to take into account for the fact that the tools are a little more primitive than what we're used to, right? Java, for example, and most major programming languages have the concept of first-class dependency management, right? You use, Gradle or Maven or some build system in your Java code, or use package.json on your Node code, and you can say, I want this dependency at this version, and it pulls it in. It pulls in transitive dependencies. You can update them. You can use them. Your IDE recognizes them, right? There's this whole ecosystem that's developed over decades to make it easy to use these off-the-shelf libraries. Most infrastructure as code tools just haven't had decades, and most of them just haven't developed this ecosystem and this idea of dependency management, this ethos of testing, and all the other ingredients that you need to make the code solid and usable off the shelf. And if you look at the open source world, in the early days, nobody trusted any open source code, right? It was, companies didn't use that stuff in production. That's garbage, right? It's crap. But a few decades later, we figured out how to build the stuff, how to test it, how to version it, how to release it. And now you'd be silly not to use open source code in your project. I think the exact same thing will happen in the infrastructure world. It's just going to take time. And I think the code is just as reusable.
Your company publishes open source reusable libraries. Could you pick one example of one of these libraries to talk about what it does and what is the value proposition?
Sure, yeah. So the company is Gruntwork, and the focus is on exactly this problem, is creating reusable infrastructure code. Because the reality is most companies go into production on Google Cloud, on AWS, on Azure. The infrastructure you need under the hood is going to look pretty darn similar. You're going to use it in a million different ways, but under the hood, you all need that VPC thing we talked about earlier. You're all going to need a database, some sort of cluster to run your workloads like Kubernetes, load balancing, DNS, CI/CD pipelines, monitoring, alerting, etc. That long list of things. And so we create a bunch of reusable code for that. Some of that code we've open sourced. One of the examples actually we brought up earlier, which is the HashiCorp Vault. So a bunch of reusable code to run Vault, this secrets management solution, on AWS, on Google Cloud, and on Azure. And the code will, for example, spin up a Vault cluster. It will, actually, even before that, it'll give you code to install Vault on a Linux server. And we typically recommend running this code in a Packer template. This is another open source tool. Basically lets you create a virtual machine image with Vault and all of its dependencies already installed and configured. Then we give you code to run a cluster of servers, and you would run your virtual machine on those servers. So now you have a bunch of servers with Vault on it. There's a script that we provide to then bootstrap those servers so they can discover each other and connect and form a nice little cluster for you. There's code there that shows you how to automatically unseal the Vault servers so that they're actually able to access the secret data that they're storing. There's code to hook up load balancers, that code to deal with TLS certificates on the node so they can all speak to each other over an encrypted connection, and so on and so forth. So this code gives you a bunch of these building blocks to run Vault. And instead of spending 2-3 months learning how to run it, learning how to secure it, learning how to scale it, and all of these other pieces, you can basically grab this code off the shelf, use it at a specific version directly from the repo, and get Vault up and running in a day. And over time, saves you a huge amount of maintenance. As Vault changes, as Terraform changes, as AWS changes, you basically get all of that through versioned releases. So it saves you a lot of time over the long run as well.
You mentioned in, I believe it was one of your talks, about these open source repositories being battle hardened and production ready. That comes about from the feedback cycle over time of people using these. People in the community submit PRs. You see how to improve them. Could you give me an example of a modification that you made from the original version of a library and the version you have now that solves some kind of production issue or otherwise improved the code?
Yeah, there's been a bunch. We've been maintaining this code now for probably 4 years. It's been used in production by hundreds of companies. And so there's been lots of interesting stories. I mean, the simplest one to understand is just the fact that, we've talked a few times that a lot of the DevOps tooling is new. And so it's evolving and changing very, very quickly. The code that you wrote that works with Terraform version 8 that was out 2 years ago does not work anymore with version 12, which is out now. So one of the biggest things we did is the library of code is 300,000 plus lines of code, is updating all of that code to work with Terraform 12. And that was a huge, massive change that took months, but we do it once and then everybody benefits. One of the other ones that I fondly and not so fondly remember is working on the Elasticsearch code. We actually caught some bugs just from having automated tests. So our automated tests, they spin up the ELK cluster, or actually about 20 ELK clusters in a whole bunch of different configurations, and make sure that we can write data, read data, et cetera. And at one point, we noticed that the tests were passing just fine in US East 1, but our test code randomly picks other AWS regions. And so they were failing in other regions. So we found a couple bugs, not in our code, but actually in Elasticsearch itself, where some of the discovery code that they had was hard-coded to use US East 1. And, there's a dozen stories. We found issues with how Kibana used TLS, and we had to check out the code and actually modified source code to find out what was going on. And there's a certain type of TLS certificate that it just doesn't work with, and you don't get a reasonable error message. And it's the kind of stuff that there's no way to expect it. It's the reason that these software projects take so long, right? We're talking about Yak Shaping, and you think you're going to be doing log aggregation, and instead you're 10,000 lines deep in Kibana code dealing with how they process TLS certificates. This is the stuff that comes from just having that feedback cycle over a long period of time.
Yevgeniy, I had planned to spend some time on testing, but we are pretty close to end of time. I do want to tell listeners the book has an extensive amount of practical tips about testing infrastructure of code. That could even be the subject of an entire episode, and maybe we'll do that someday. I want to wrap up with, where can people find you on the internet, or anything you want to point people at?
If you're interested in finding me personally, in hopefully a not creepy way, I have a homepage, which is ybrikman.com. If you Google my name, it should be the top result if I've done my SEO correctly. And if you're interested in learning anything else about my company and the work that we're doing, the company's called Gruntwork. If you Google us, we should also come right up, but it's gruntwork.io.
Now, Ed, your book is available in the usual places where people can purchase books. So
yes, thank you for that. Yep, Amazon and Barnes & Noble and your local bookstore, you should be able to find it.
Yevgeniy, it's been a pleasure speaking with you about infrastructure as code. And thank you for talking to Software Engineering Radio.
Thank you so much for having me. This was a lot of fun.
For Software Engineering Radio, this has been Robert Blumen, and thank you for listening.
Developers, take your marks. It's time to upgrade your data platform to InterSystems Iris. It's time to deliver complex mission-critical applications in the fastest route possible. It's time to use any data from any source. It's time to embed analytics and create interactive user interfaces. So what are you waiting for? Choose your language, choose your tools, choose your environment. Collaborate, build faster, and deploy more efficiently. Done and done. Tomorrow's next breakthroughs are waiting for you today. InterSystems Iris Data Platform, the fastest way to build applications. Ready, set, code. Start coding for free. Visit intersystems.com/try to try Iris. Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.